This video is about influences on logical positivism. And I want to focus on a couple of influences that are not really emphasized that much in the articles by Suppi and Rosenberg that you've read. The first influence is mentioned, and I want to say just a few more words about it, and that's this idea of having a system of first-order logic as a sort of perfect language. And I want to talk a little bit more about what that's all about. And then separately from that, as a distinct issue, I also want to talk about the influence on logical positivism from Einstein's special theory of relativity. And although these might seem to be completely different things, the key concept that brings these together is that both of these play a really important role in trying to understand meaning for the logical positivists, in trying to understand what is the meaning of something that we say in science. And I just want to bring that out a little bit more than what was discussed in the articles by Suppi and Rosenberg that you read. So let's start first with first order logic and talk a little bit about what that's all about. And I want to start with a very, very simple example. Some of you already know what first order logic is, and you've seen it maybe in other courses or in other contexts. But if you're new to logic, you might have seen some symbols in the articles by Rosenberg or Suppi that you just weren't quite sure what they meant or what they were supposed to do. So let me start with a very, very simple example and show you how first order logic is a formal language into which we can translate statements that are expressed in any natural language, and specifically the logical positivists were interested in translating statements in scientific theories into this formal language. So let's start with a pretend statement in a scientific theory. Okay, it's a pretend statement because this is not the kind of statement that you would actually find in a scientific theory, but it might look something like this. Suppose I say, if the electron is negatively charged, then it will deflect upwards. So imagine a very simple sort of experimental situation in physics where you have an electron beam going through maybe magnetic plates, and the claim is that if the electron is negatively charged, then it will deflect upwards. And then we can add another statement to turn this into the beginnings of a piece of reasoning or an argument. We can say, well, now let's suppose that the electron is negatively charged. Then what I can conclude from that is that the electron will deflect upwards. It's a very, very simple example of the kind of reasoning that in ordinary baby logic we call modus ponens. And we can exhibit the logical form of this argument by doing the following. What we're going to do is we're going to replace entire sentences with single letters. So for instance, for the sentence that says the electron is negatively charged, well, you'll notice appears in exactly two places. It appears in that first place I just underlined and in this place here. We're going to use the letter N. And then for the sentence that the electron will be deflected upwards, this one here, that appears in exactly two places, and we're going to call that sentence D for deflection. And so now what I can do is write out this same argument, but translate it into a formal language that has a very rigorous syntax. And what that looks like is maybe something like this. I can say if n then D, N, therefore D. And now what I've done is I've taken an argument that is expressed in the language of science and abstracted away all the content and turned it entirely into symbols. Now, the value of doing this is that there are paper and pencil methods that we can use on this side, on this symbolic representation of the argument, to determine whether or not this argument is what we call a valid argument. And in this case, of course, it will turn out to be valid. So what the logical positivists were really impressed by was the development of this kind of formal language in here, which occurred most significantly with the publication of Bertrand Russell's Principia Mathematica in 1910. And this very, very simple version of the language that I'm showing you can also have a much more refined side to it. We can make it a lot more subtle and complex if we add to it the ability to talk about generality. So here's an example of what that would look like. So suppose I want to make a general statement about electrons. I'm not just talking about this particular electron here, but I want to say something like all electrons are negatively charged. How can I express that in my formal language? Well, some of you have seen this kind of thing maybe in mathematics or in a course in formal logic. We can express it like this. We can say, well, for any x, if x is an electron, then x is negatively charged. And now I can take statements that are written like this in this formal language and subject them to paper and pencil manipulations to determine whether or not the reasoning that they're involved in is deductively valid. So now, the point about all this is not that you're going to have to write out symbols for sentences like all electrons are negatively charged, unless you come and take my symbolic logic course with me sometime. The point is that what the logical positives believed is that when we ask, what does it mean to say that all electrons are negatively charged, we can do that in sort of two steps. The first step is to write it out as a symbolic sentence in a formal language. And that will clear away a lot of the confusions that are implicit in our ordinary ways of talking. So they wanted to turn scientific discourse into something that was written in a very, very precise way. That's the first step. The second step is that I need to somehow convey what is the meaning of the term electrons and what is the meaning of the term negatively charged. And for that, what the logical positivists said is we have to connect these terms somehow to experience. And it's in trying to establish that connection that the logical positivists use what you've seen already described as correspondence rules. Okay? So the main point here is simply that the language of logic was supposed to be a kind of perfect language, because if we expressed everything in our scientific theories in this symbolic notation here, then no one could ever misunderstand what we mean, so long as we tell them, for instance, that Ex means X is an electron, and Nx means X is negatively charged. If I give you that sort of decoder ring, and then I give you this symbolic expression up here, you cannot possibly misunderstand what I'm saying. So it would be a perfect language in the sense that there would be no ambiguity in our communication. And wouldn't it be awesome if we could communicate science in such a way that no one would ever misunderstand what the scientific claim is that is being made? And that's really what is the sort of philosophical core of this desire of the logical positivists to rewrite scientific theories in the language of first order logic. It was like a project, it was like a proposal for something that philosophers could do in order to help clarify meaning. Clarifying meaning was a crucially central feature of what logical positivist thought philosophy could do. And part of the way they came to view that or to see that or appreciate that was by looking at the work of Albert Einstein, and specifically Einstein's work on special relativity.